Today we're going to explore one of the most fascinating and counterintuitive phenomena in nanoscale physics, the reversible plasticity paradox in metallic nanocontacts. Before we dive into the paradox, let's review what we know about plasticity at the macroscopic scale. In classical materials science, when you deform a metal beyond its elastic limit, it undergoes plastic deformation. This deformation is permanent and is mediated by dislocations, which are line defects in the crystal structure. Here's a simplified view of a metal crystal. The red dots represent atoms in a regular lattice. When stress is applied, dislocations move through the crystal, causing permanent atomic rearrangements. The key principle of classical plasticity is that once you've deformed the material, you cannot simply reverse the process by removing the load. The atoms have moved to new equilibrium positions. But here's where things get really interesting. When we scale down to nanometer dimensions, something completely unexpected happens. In metallic nanocontacts, typically just a few nanometers in size, we observe plastic deformation that is fully reversible. This directly contradicts everything we learned from classical dislocation theory. Let me first explain what we mean by metallic nanocontacts. A metallic nanocontact is essentially a tiny bridge of metal atoms connecting two larger electrodes. The contact region can be as small as 1 to 10 nanometers, containing just a few hundred to a few thousand atoms. How do we know that reversible plasticity occurs? Let's look at the experimental evidence. Scientists use a technique called mechanical break-junction. You start with a thin metallic wire and gradually stretch it until it breaks, creating a nanocontact just before the final rupture. As you stretch and compress the nanocontact, you measure its electrical conductance. Conductance is extremely sensitive to the atomic configuration of the contact. When you stretch the contact, the conductance changes as atoms rearrange. But here's the amazing part. When you compress it back, the conductance returns to its original value. The atomic structure has reversibly deformed. So why does this reversible plasticity occur at the nanoscale? What's so special about being small? At the nanoscale, surface effects become dominant. The surface-to-volume ratio is enormous, and surface stress plays a crucial role in the mechanical behavior. The surface-to-volume ratio scales as 1 over r, where r is the characteristic size. As you make the contact smaller, surface effects become exponentially more important. For a typical nanocontact of 5 nanometers, approximately 40% of all atoms are at or near the surface. Compare this to a macroscopic object where surface atoms are negligible. The second key reason is that at such small sizes, it becomes energetically unfavorable to nucleate dislocations. The energy cost of a dislocation is proportional to GB squared L, where G is the shear modulus, B is the Berger's vector, and L is the length of the dislocation line. In a contact that's only 3 nanometers across, there's literally not enough space to accommodate a complete dislocation. The contact is smaller than the typical dislocation core size. The third reason involves the elastic stress fields generated by the surfaces. Surface stress creates an inward pressure on the nanocontact. This stress field acts like an elastic restoring force that can push atoms back to their original positions when the external load is removed. The surface stress is approximately 2 gamma over r, where gamma is the surface energy and r is the radius. For smaller contacts, this pressure becomes very large. Let's do a numerical calculation for a gold nanocontact to see how large these effects really are. The surface energy of gold is approximately 1.5 joules per square meter. Let's consider a contact with radius 2 nanometers, which equals 2 times 10 to the negative 9 meters. Plugging into our formula, the surface stress is 1.5 gigapascals. This is an enormous pressure, comparable to the yield stress of bulk gold. This massive surface stress acts like a built-in spring, always trying to restore the contact to its minimum energy configuration. There's also a subtle quantum mechanical aspect to this phenomenon that we shouldn't ignore. In nanocontacts, electrical conductance is quantized in units of G0, the quantum of conductance. G0 equals 2e squared over h, which is approximately 7.75 times 10 to the negative 5 Siemens, where E is the electron charge and h is Planck's constant. Each quantum of conductance roughly corresponds to one independent channel for electron transport through the contact, typically associated with a single atom or a few atoms. Electrons flowing through the nanocontact must pass through discrete atomic arrangements. Each stable configuration corresponds to a specific conductance value. The reversibility we observe means that the nanocontact is returning not just to a similar structure, but to exactly the same quantum mechanical configuration. How do we theoretically understand and predict this behavior? The main tool is molecular dynamics simulation. Molecular dynamics simulations solve Newton's equations of motion for every single atom in the system, typically using empirical potentials to describe atomic interactions. The force on atom I is the negative gradient of the potential energy U with respect to that atom's position. Then we solve Newton's second law, mass times acceleration equals force, for each atom independently. These simulations beautifully confirm the experimental observations. When you apply and remove stress cycles, the atoms return to their original positions with remarkable fidelity. Perhaps the most insightful way to understand reversible plasticity is through the energy landscape picture. Imagine the nanocontact as a ball sitting in an energy well. The bottom of the well is the ground state configuration. Under applied stress, you push the ball up the energy landscape. The key insight is that for nanocontacts, this energy well is both deep and steep. The surface stress creates a strong restoring force. When you remove the external load, the system naturally rolls back down to the energy minimum, returning to exactly the same atomic configuration. Now you might ask, what happens if we deform the nanocontact too much? Is there a limit to this reversibility? Yes, there is definitely a limit. If you stretch the contact beyond a critical strain, you'll reach a point where the system crosses an energy barrier. Beyond this critical point, the contact will irreversibly rupture or undergo a permanent structural transformation. The reversibility only holds within a certain strain range. For typical metallic nanocontacts, the critical strain is approximately 0.1 to 0.3 or 10 to 30%. Beyond this, irreversible changes occur. Does this phenomenon occur in all metals? Or is it specific to certain materials? Reversible plasticity has been observed in gold, silver, copper, platinum, and palladium nanocontacts. These are all FCC metals with relatively low stacking fault energies. The surface energy gamma is the key material parameter. Metals with higher surface energies show stronger reversibility because the restoring force is larger. Gold has a surface energy of about 1.5 joules per square meter. Platinum has a higher value, around 2.5 joules per square meter, which means even stronger reversibility. Let's talk about why this phenomenon matters beyond pure scientific curiosity. What are the practical implications? Reversible plasticity could enable nanoscale mechanical switches and sensors that undergo many deformation cycles without degradation. This opens the door to self-healing nanodevices. Imagine a nanoelectronic circuit that can repair itself after mechanical damage by simply relaxing back to its ground state. From a fundamental perspective, this helps us understand the ultimate limits of material strength and ductility at the atomic scale. This phenomenon dramatically illustrates how mechanical properties are fundamentally size-dependent at the nanoscale. You cannot simply scale down bulk properties. Interestingly, there's a connection between reversible plasticity and biological systems. When you stretch certain proteins, they unfold. But when you release the tension, they refold back to their native state. This is conceptually similar to reversible plasticity. Both phenomena involve energy landscapes with deep minima corresponding to stable configurations and reversible excursions away from these minima under applied force. Here's a schematic of a protein. Under mechanical force, it unfolds into an extended chain. Release the force, and it refolds. Nature has been exploiting reversible nanoscale mechanics for billions of years. Studying reversible plasticity experimentally is extremely challenging. Let me explain why. First, you need to create and stabilize nanocontacts. These are inherently fragile structures that exist only under carefully controlled conditions. The experiments must be performed in ultra-high vacuum to prevent contamination. A single adsorbed molecule can completely change the mechanical behavior. You need sub-angstrom precision in mechanical positioning. We're talking about moving things by fractions of an atomic diameter with high stability. While we can measure conductance easily, Actually imaging the atomic structure in real time during deformation is extremely difficult. Most of our atomic level understanding comes from simulations. Despite significant progress, several important questions remain open. What exactly determines the maximum reversible strain? Is it a universal threshold, or does it depend on the detailed atomic structure of each contact? How does temperature affect reversible plasticity? At higher temperatures, thermal fluctuations might help or hinder the reversibility. Can we engineer nanocontacts with enhanced reversible plasticity by choosing specific crystal orientations or alloying elements? Let's do a direct comparison between macroscopic and nanoscale plasticity to really drive home how different things are. On the left, we have macroscopic plasticity, irreversible, dislocation-mediated, surface effects negligible, bulk properties dominate. On the right, nanoscale, reversible, surface-dominated, no dislocations, quantum effects important. Can we write down a mathematical description that captures the essence of reversibility? The total energy is a function of all n atomic positions R1 through Rn. At equilibrium, this equals E0, the ground state energy. Under small displacements delta R, the energy increases quadratically. Kij is the effective spring constant matrix connecting atoms I and J. Reversibility means that when you remove the external load, the system spontaneously returns to E0. The energy landscape has a unique, deep minimum. At equilibrium, all forces vanish. The derivative of energy with respect to each atomic coordinate equals 0. Let's think about the timescales involved in these deformation processes. In typical experiments, the strain rate is about 1 nanometer per second. For a 5 nanometer contact, this means a deformation rate of about 20% per second. Meanwhile, atoms vibrate with a period of about 100 femtoseconds. That's 10 to the 13 vibrations per second. The ratio of experimental timescale to atomic vibration time is about 10 to the 13. This means atoms have plenty of time to find their optimal positions during deformation. This huge separation of timescales allows a system to remain close to quasi-static equilibrium throughout the deformation process, which is crucial for reversibility. What about defects? In bulk materials, defects like vacancies and grain boundaries are everywhere. How do they affect nanoscale reversibility? One amazing aspect of nanocontacts is that they can be essentially defect-free. With only a few hundred atoms, the probability of containing a defect is actually quite low. If the nanocontact forms as a single crystal with perfect FCC structure, it has no grain boundaries. This is very different from bulk materials which are typically polycrystalline. The absence of defects is actually crucial for reversibility. Defects could act as nucleation sites for irreversible structural changes. Let's think about this from a thermodynamic perspective. What does reversibility mean in terms of thermodynamics? In thermodynamics, a truly reversible process has zero total entropy change. The system returns to exactly its initial state. The entropy change of the system plus the entropy change of the surroundings equals 0 for a reversible process. However, we need to be careful. The deformation of a nanocontact is not reversible in the strict thermodynamic sense. Some energy is dissipated as heat. What we mean by reversible plasticity is that the atomic configuration returns to its original state, but the velocities and thermal energy may have changed. It's reversible in configuration space, but not necessarily in full phase space. Where is this field heading? What are the exciting future directions? One direction is exploring nanocontacts made from alloys or multiple elements. How does chemical complexity affect reversible plasticity? Developing techniques for in situ transmission electron microscopy observation during mechanical testing would be revolutionary. Direct atomic scale imaging during deformation. Using machine learning to predict which atomic configurations will exhibit reversible plasticity could accelerate materials discovery. Integrating reversible plastic nanocontacts into functional nanoelectronic or nanomechanical devices is a major engineering challenge with huge potential payoff. Let me summarize the key takeaways from our discussion of the nanoscale reversible plasticity paradox. First, classical plasticity, based on dislocation theory, completely breaks down when you reach the nanoscale. Size truly matters. Second, surface stress and surface energy become the dominant factors controlling mechanical behavior, creating strong restoring forces. Third, dislocations, the workhorses of macroscopic plasticity, simply cannot form or operate in volumes smaller than a few nanometers. Fourth, the nanocontact exists in a deep energy well, and deformation corresponds to reversible excursions away from this minimum. Fifth, quantized electrical conductance provides an exquisitely sensitive probe of the atomic scale structure, allowing us to detect reversibility. And finally, this phenomenon opens up exciting new possibilities for self-healing nanodevices and ultra-durable nanoscale mechanical components. The nanoscale reversible plasticity paradox beautifully illustrates a fundamental principle of nanoscience. You cannot simply extrapolate bulk properties down to the nanoscale. New physics emerges. Nature is full of surprises when you look at the nanoscale. What seems impossible from a macroscopic perspective becomes not just possible but natural at atomic dimensions. This is exactly why nanoscience and nanotechnology are so exciting and important. We're discovering entirely new phenomena that could revolutionize technology.